welcome to everybody. Welcome again. I'm Cristiano. I'm the lead AI scientist here at PySchool. And today's Tech Talk, it's a pleasure to host Alberto Cazzaniga. Alberto has a PhD in pure mathematics at the University of Oxford, and currently is a permanent researcher at the Area Science Park in Trieste. He's pushing research mainly focusing on application of AI, deep learning techniques in life science and material science. And together with me is a lecturer at the Master in High Performance Computing in Trieste. The Master in High Performance Computing, it's a master from SISSA and the International Center for Theoretical Physics, and we share together some courses in machine and deep learning. So today, Alberto will introduce us to the geometry of large language model representation, which is basically a very interesting topic, given that Alberto is a mathematician. So it's a pleasure to hear about the geometry of this kind of models and architecture. So welcome again, Alberto. I will leave you the floor.
Thank you so much, Cristiano. Thank you for the introduction, and thank you to PySchool for giving me the opportunity to present our work here. But again, I want to stress even more, wait a second, that I want to thank Cristiano for giving me the opportunity to present in one of the hottest week for a researcher in deep learning, as can be seen from this tweet that I hope you see, where someone is saying that happy annual Contemplate Quitting Machine Learning Research Day, because some review of an important conference came out. And in fact, I will say even week, because we are currently under review. But thanks God, I have amazing collaborators that are doing experiments and writing reviews while I'm giving this talk. Before starting the real talk, I just want to give you a brief introduction to where I work, starting from the Wall Research Institute, Area Science Park, which is sited in Trieste, which is a beautiful city that Cristiano, I'm sure, loves very much as I do. And we sit on the hills that give on the city and on a wonderful landscape with the seaside. In particular, I focus on three main things in the last 40 years or so. First, building a powerful research infrastructure, of which probably the most important part is the synchrotron, the only Italian synchrotron here in Trieste. And then it grew a scientific park dedicated essentially to technology transfer, so to the development of cutting-edge technologies and implementation inside the companies. And there are a bunch of startups that are based here in our science park. But in the last 3 years, which is more interesting for the talk of today, a new division was opened that is focusing on fundamental and applied research. In particular, we have a lab which is called LADE, Laboratory of Data Engineering, that focuses essentially on the whole computational part that concerns the data-driven research project. So starting from maintaining computational infrastructure, to organizing data collection to the best of the state of the art, and then developing cutting-edge models, especially based on machine learning and deep learning techniques, to eventually go back and foster further research discoveries and speed up, let's say, laboratory findings. In particular, we collaborate with two other sub-institutes here in ADE, two other groups. One is LADE, which is Laboratory of Genomics and Epigenomics, which is the cause of our obsession with sequences, and in particular genomics and proteomics sequences. And then LAME, which instead is based on advanced material discovery through electron microscopy, and that is leading us back to the study. And it's more recent, and is leading us back to the study of images, where all of us essentially in our lab come from. And here I just want to give you a brief uplight of what happened in the last 3 years, thanks to quite a few rounds of fundings, both in national and international. We started with 5 people essentially, which many of are my collaborators. And then we're growing and growing, and this is the last 3 years, and I'm actually skipping few photos because it's kind of becoming difficult to keep up. So it's a great place to work. They were very young, very active, and always looking for collaboration. But let me now get to the proper content of the talk. And of course, before I want to say that I'm a little bit out of shape with the online talks, so please do find your best way to interrupt me if you don't understand, and I'm very happy to take questions along the way. So the talk of today essentially will be focusing on the following situation. When we have essentially to fix a neural network architecture is equivalent to choose a certain family of function. And in particular, this family of function typically is made by is obtained by the composition of much more elementary functions that bring us from one layer to the next, and that are typically of very similar form, not exactly the same because dimension can change, but typically are classically made of multiplication by a matrix, addition of a bias, and application of a nonlinearity component-wise. Okay, we can think about a problem such as classifying handwritten digits, so the MIS dataset, or classifying images from the ImageNet dataset, so distinguishing cats, dogs, and boats and airplanes. But eventually what happens if someone smart enough trained this neural network, fixed a certain number of parameters in order to obtain finally a function which has the principal objective of given a datum, which is essentially a vector corresponding to an image, to decide if this image belongs to one class or another. So to decide if an image corresponds to a 9 or a 5, or to decide if an image is a cat or a dog. Now, in the last 10 years, there has been a lot of research in studying what are the single transformations, what are the effects of the single transformations of the data inside these layers, and how they are related to understanding fundamental concepts and to eventually to solve tasks such as classification. In particular, the way in which we want to look at this is the following. Each data point can be considered as a vector in a very high dimensional space. Now, if we have a whole data set, this is going to correspond to a point cloud. This point cloud is going to be transformed by this function, and we want to follow the geometric transformations all along the way. Typically, again, this has been related to ability of linearly separate our data set to distinguish classes, or to getting insights such as the fact that the nearest neighbor of certain images belong to compatible classes. In particular, what we want to do is to ask the following question. And we want to ask if understanding the geometry of the transformation of a data cloud now applied to a particular type of architecture that has been very popular in the last few years, which is the one of large transformers models, can give us some insight on how meaningful features for data are, first of all, found and then exploited. Of course, we do know that meaningful features arise because we all know the latest developments in large language, for instance, in the NLP domain, such as GPT or Llama or other architecture. It's evident that these models are able to encode meaningfully text, but we do want to understand how this happens all along the way. So the way all of this is going to be based on two main work. The last one is still under supervision in collaboration with one researcher of us, which is one PhD of us and shared with the university, which is Lucrezia Valdiani. Recently hired a researcher that was before PhD in SISSA, that is Diego Doimo, that was supervised by Alessandro Daio, which is also our collaborator, and by Francesco Cutudello, which is researcher real, and Alessio Suini, that is maybe my longest and more stable collaborator. Again, I want to stress that this also was presented last year at the NIPS workshop in machine learning for structural biology, because we addressed firstly this problem in the context of the study of protein sequences here in ADEA, with actually obtaining some biological applications. The way in which we are going to be tackling this question is the following. First of all, I want to give you some insight on the models that we consider. So I will give a somehow naive introduction. I mean, I'm not going to go into all the details, but I will highlight the most important parts that will be care about large transformers. Then I will move to try to explain what we intend by geometry, and in particular by local and global geometry, and why we're interested in their interplay. And lastly, I will present our results, highlighting mainly two facts. First, that local and global geometry are tightly related, and secondly, that the fact that we can study the geometry can help us in understanding which are the layers which are mostly informative with respect to some semantically meaningful tasks. Last but not least, since I changed my title from large transformer to large language models, I will give you some update on some very recent results that we obtained on representations from large transformer models now applied in the context of NLP. And we'll see that somehow they confirm at least part of our findings. So typically, if I would have to describe a deep learning model, I will start from data, because data is the essential component that allow us to build up an effective learning machine. But in this case, I want to start the other way around. I will start from the task, because it's what in the context of large transformers, what allows us to have such large data sets. The way in which I want to present it is essentially from a couple of language games. I steal the name from Wittgenstein, from which much of the NLP research somehow is partly related. And the first task is probably well known, is mask language modeling. So essentially, we're filling the blanks of sentences. We have a full sentence, we mask some tokens, and we want to predict them. We all did this game when we were learning some new language. I mean, in our case, English, for instance, in Italy. But of course, it's the same for any other language. And typically, what happens is that you start from a sentence. For instance, I bring my blank to the park, and you want to predict the blank. Now, this is quite hard. For sure, you're going to try to get some insight from the words that there are in the sentence. So bringing and then park. So bring it can lead to an object or to a person, I don't know, in a metaphorical sense, and the park is going to give us some context in deciding this word. So but still it's quite vague, because we could think about something like a ball, a book, or a daughter, or a friend, and still, so the task and the perplexity we have in solving this task is quite hard. Of course, the way in which we choose to fill in this blank depends on our experience. For instance, here in Trieste is a city full of researchers, so someone is very likely to bring a book or a laptop to the park, but it's also a city where there are quite a few old people, so it's also possible that someone brings his granddaughter or his grandchild to the park, okay? The more the context, the easier to solve this task is. I bring mine to the park to run, I will bring probably my dog or my shoes. Still, the perplexity is quite high. Again, the more we focus, I bring mine to the park to play football. This could be a friend or a ball, for instance, but football contextualize our choice. And finally, if there is enough information, then the choice is almost certain. I bring mine to the park to play with other puppies. This is going to be almost for sure a dog. Okay? This is nothing else than the strategy that was used to train the model BERT some few years ago, which is the bidirectional encoder representation. Paper is like bidirectional encoder representation from transformers. The other notable task, which became very popular the last few years or months, is predicting the game of predicting the next word. This game starts in principle without context. So you want to generate a sentence which makes sense without having any other information. And for instance, this is a game that I kind of like because we are humankind. We are quite a selfish species. So typically a sentence might start with I. Then we can go along. There are many different directions in which we can go, but then it could be that we go along with a sentence with I bring. And then we continue, and once we have enough context, I bring my book to the park too, then the completion is almost certain because everyone will answer, I bring my book to the park to read. Okay, perfect. Every one of us relates this task to GPT, of course, nowadays, but this comes from a long way. The first time, one of the first times it was applied in the context of deep learning is at least in a paper of Benjo from 2003, an error probabilistic language model, but this task was already out there in the, let's say, computational linguistic community before. And I want to conclude this catch introduction with a sentence from, in fact, a long time ago that says that a word is characterized by the company it keeps, and it does it in two ways. First of all, it is characterized by the words within the sentences, which is a sort of internal context, but is also characterized by the context of the whole corpus, so by other sentences somehow in the corpus, okay? So today we're going to be studying transformers, and here is a very quick upshot of what these are. I'm quite general, but then I will specify a little bit. So the input, again, I'm giving this in the case when we're trying to predict the next word. So we give a partial sentence and we want to predict the next word. So I bring the book to the part 2, and then we want to predict read. So first of all, the sentence is translated in vectors, which are one-hot encoded, and then embedded in some fixed dimensional vector space. And then we have essentially a transformer consists of a function f of theta that transforms this vector in another vector that is used via classification head to classify which is the most likely word in the dictionary to follow the piece of sentence that we gave. So for instance, in this case, we're going to be having a low probability for the word eat, but a very large probability for the word read. Again, in particular, I want to stress that this transformer is made of a certain amount of functions, f theta 1, f theta 2, f theta n, which are these essentially these self-attention blocks, which of course have different parameters, but they're all of the same functional form. So essentially, we can see them as an elementary functions that go up and in the end constitute a transformer. So again, I want to stress one thing, that the self-supervision allows to train on very, very large data sets. Essentially, we should assume every time that we see now a large language model that it has seen basically anything that has been written and encoded electronically by humankind, more or less. And second of all, again, I want to stress that the transformations of each self-attention block transform a vector, typically lying in a very high dimensional vector space, probably of thousands of dimensions, in another vector, and then in another vector, and again until we get to the end. And all of this transformation have the same functional, belong to the same functional family. Okay? A couple of words, I will feel guilty without mentioning anything on self-attention. So I want to spend a couple of words on that and basically describing the key component of one of these blocks B. Okay? So the self-attention is revolutionary from 2 points of view. If we think about a classical neural network, let's say multi-layer perceptron, we have one single input vector, okay? And the basic transformation, which brings us from one layer to the other, is absolute. So essentially corresponds in multiplication by a matrix, an application of a nonlinearity. The matrix, though, does not depend on the input. The matrix, once the training has been done, is absolute, and even the choice of nonlinearity. Transformers are quite different, and in particular, the self-attention operation is radically different. First of all, the input is not a single vector, but a frame or a set of vectors, x1 to xn, so it's particularly suited for studying sequences, but also other type of data. And second of all, the elementary transformation, which is still going to be given essentially by multiplication by matrix, more or less, is relative. So it depends on the context. It depends on the mutual relationship between tokens. In particular, one constructs a set of coefficients, alpha I, which essentially depend on the, here is simplified by linear product on the relation. Let's say they encode the relation between token I and token J. And then the transformation is just a linear combination of the various representations. At each stage, the transformation is given by a linear combination weighted by these coefficients of the representations of all the tokens. Of course, I mean, this was introduced by in the seminal work "Attention is All You Need" in 2016 by Vasvani and other collaborators. But of course, one can raise the following questions. The following question: we know that transformers have large number of parameters. For instance, GPT has billion and trillions of trillion of parameters. Where are all these parameters coming from? From this presentation, of course, I did an oversimplification. The inner product is not sufficient to encode all the information that we want. We introduce some learnable weights, which are typically called as a query, key in the attention construction, and value to update the value of every single representation. And these are, of course, projections, essentially linear projections, that decide essentially the transformation, depending, again, what is crucial, on the mutual information between the tokens. So we can imagine WQ as asking a question about a token, and WK essentially deciding which token is mostly relevant in answering this question. And this a very celebrated example shows that in translation tasks, when you invert the ordering of words because you are changing language, for example, zone économique européenne, that is translated in European economic area, inverting the order of the word, is described by the fact that attention weights are essentially anti-diagonal. Okay. But the cases in which we focus primarily are not, I spoke only about language, but the cases that we started to analyze are actually coming from different domains. The first one is the domain of protein sequences, where large transformers played a crucial role in scientific development in the last 2 years, essentially. And the reason for implementation of transformer-like models in this context is more or less the following. When we're interested in proteins because, of course, they play a key role in biological mechanisms, and in particular, we're interested, given a protein, in understanding its function, so its role in our body. But a protein can be described in 2 ways. It can be described as by giving essentially its structure, so essentially its approximately its atomic disposition in the 3D space, or it can be described even as just as a sequence of amino acids. So essentially as a string of letters. And the 2 are not quite equivalent. The structure is, knowing the structure is almost not quite the same, but almost the same as knowing the function, while knowing only the sequence is a much less informative information. And in the last few years, a lot of attention has been put in trying to predict, in fact, the 3D structure of a protein from only the string of amino acids for the following reason. We know a very few number of structures, around 200,000, while we know a very, very large amount of sequences, because sequences can be deduced from genomics experiments, which are very, very cheap, while structures necessitate a much more difficult type of experiments, typically crystallograph experiments, which are much more expensive and slow to be computed. So the idea that was at the base of one of the basic ideas at the root of AlphaFold, that was one of the most popular, AlphaFold 2, one of the most popular deep learning architecture developed in the last few years, was essentially to exploit the large amount of sequences to then, in a self-supervised way, understanding more about the structure. These have been taken at somehow at an extreme by a group protein group at Meta, for which we're gonna take inspiration. I mean, for which we're gonna like the models today, models that go under the name of ESM modeling models, so evolutionary sequence modeling. In particular, the game we play for proteins is, given a protein, we know its sequence, okay? We can assume we know its sequence. We mask randomly some amino acids, and eventually we want to predict their identity. So for instance, here we're masking an L, the model is behaving well, and I'm predicting with 90% that the missing token is an L. The way in which we do it, we just again apply successively a certain amount of detection block, and at the end, we attach a classification head. Our results are essentially focused on describing representations after each one of these attention blocks. So it's important to notice that every time that we have a sequence, we're going to have not only one vector in high dimension representing it, but a bunch of vectors, one per each element of the sequence. So one per each of these amino acids. So a T will correspond to a vector and L to another one, which of course depend on the context. But somehow this information is a bit overwhelming, and typically in the literature, a brutal simplification has been done where one takes the sequence, the average along the sequence axis, okay? So you take the average so that at every amino acid sequence or to every protein, one associates a single vector lying in a typically quite high dimensional space. And then we follow, essentially for each protein, and for each protein in a data set, we will follow these representations after successive attention blocks. Okay? So this is the description of the models in the case of proteins, while we consider different model much more inspired on GPT-like type of task in the context of images. In particular, we study eGPT, described in the paper Generative Pre-training from pixels of 3 years ago, where the following architecture is described and then trained and analyzed. First one starts from an image. An image can be broken up in a certain number of smaller sub-images just by cutting it evenly. We have a downsampling by averaging on this smaller part, on these smaller blocks of the averaging pixels on this smaller block of the images, and considering essentially simplification of the color code. Once the image is simplified, so downsampled, one encodes the image in a certain high-dimensional vector space, and then in a raster fashion, one stretches the images by considering successive pixels. So to every pixel, we will have associated a vector, and we put this in a sequence where we have here the arrow representing the sequence axis. Okay? Again, the sequence is transformed by an identical attention block. In this case, the difference with the situation for proteins is that we're going to be considering causal attention, so where only part of the sequence is shown in order to make to predict the next representation. And this is done because the final task is the one of predicting the next pixel. Okay, given a certain amount, given a certain portion of the image, for instance, we could be considering having I don't know, this part of the image. We want to try to predict this next pixel here. Okay, I hope you see my pointer, otherwise we're in trouble. But
sorry, Alberto, I lost one piece. How does the encoding works from the RGB picture to the first block? On the left of the image, there is an encoding.
I know this is a learned encoding. Okay, learned. Yeah, essentially this is like so you downsample the image. And this is the learned positional encoding, okay? It's like essentially now these pixels are not quite pixels because they're squares of the image. I mean, they represent a square of the image, but each one of those is embedded in a certain dimension by a learned linear embedding, essentially, okay? Thank you for the question. If there are other questions, please stop me, okay? And yes, I think I said more or less what I wanted to say. And again, in the literature, still we have essentially it's accepted in the literature to consider sequence average again. So once we consider this image as a sequence of blocks, a stretched sequence of blocks, portions of this image, to squeeze the sequence axis to obtain a single vector as a representation. This has been already used in the original paper of Chen and other collaborators at OpenAI. Okay, so what we're doing is kind of like sounded, but again, if you have questions about this average, I'm happy to answer maybe at the end. Now I want to, so these are the two models we consider, and we want to study geometric representations in hidden layers, okay? And the way we do it is with two techniques, essentially. The first is a global technique, which will be concerned in studying the dimension of the data cloud. In fact, despite the fact that our data, I mean, given a data set, we can look at this data set embedded in this high dimensional vector space, but it's empirically proven, at least, and hypothesized that this data doesn't I mean, it's clear that this data doesn't occupy the whole space, but also more is believed to be true, that is the fact that the data lies around a smaller dimensional manifold. In the linear setting, we would imagine something like, okay, maybe we have a three-dimensional space, and then our data lies on a line, and this is at the root of the fact that we use for years and years in the machine learning community PCA. But in fact, it's well known also that this manifold is nonlinear. So in fact, this is much more, we should have in mind something much more as a circle, or maybe as a sphere, or as a torus, if you know what it is, or a donut, if you know what it is. But essentially, when one studies the dimension, what you want to determine is how many given a point in your data set, essentially in how many three directions you can move without going out of the distribution of the data, okay? And it turns out that this intrinsic dimension typically is much, much smaller than the embedding dimension. We're speaking about differences of at least one order of magnitude. Typically, we embed data in thousands of dimensions, while the intrinsic dimension that we measure is typically in the order of tens, maximum hundreds, okay? I'm not going to go so much in depth in the technique, which was developed by Facco, Rodriguez, and Layo a few years ago, and that we employ basically because it's a quite effective and fast technique that you can find in a repo on GitHub that is called DataPy, and is maintained by this group, by the group of Alessandro Layo and SISSA. And it's very effective because it allows you to estimate the intrinsic dimension just looking at originate first and second neighbors, and now just at a certain distinguished amount of neighbors. So essentially, given a point, you might be looking at the, I don't know, fourth and eighth neighbors of that point in order to produce a reliable estimate of the intrinsic dimension. Again, I'm not going to go into the details unless you have some questions at the end, but I hope that at least the basic concept of what we're trying to measure is clear. Okay, mathematically, we're trying to measure the dimension of the manifold where data is supposed to lie. Of course, life is not perfect. There's going to be some noise, so we should not think about an interpolating manifold, but rather as an approximate, like an approximate. Okay. Of course, this technique is not perfect as any other technique that is statistical. It has some limits. First of all, scale matters when we measure. So, for instance, in the case of we consider a spiral with some noise. Of course, if we don't go too much close, this is going to be looking at something one-dimensional. But if you zoom in very, very much, then the distances become similar to the noise. And so you're going to be observing something which is, in fact, two-dimensional rather than one-dimensional. So the way in which you end up with a single intrinsic dimension is by considering phenomena that are persistent. So if at many scales I measure the same dimension, I will say that this is the typical dimension of my dataset. And it also has some drawbacks, such as in the case that I did very, very large, it tends to underestimate, but this is not too much relevant in what we consider. The second type of geometry we identified instead as local. Okay, here you find a couple of difficult formulas that I try to explain. So if my explanation is not clear, please do ask me. So neighborhood overlap is a measure that allows us to compare different layers in neural networks. In particular, suppose that we have a data set that is labeled by indices. Maybe we take the first point, and then this first point is going to be represented in two different ways, in the first and in the second representation. Let's say representation L and representation M. When I look inside representation L, I can do the operation of finding the k nearest neighbors of this first point. Okay, these are going to carry some indices I1 to ik. Let's say k is equal to 10. So I look at the 10 first closest point in representation L to I, and I record my indices I1 to I10. I do the same for representation M, and I record the indices J1 and Jk, which are closest to the representation in layer M of point 1. Now, what we can do is simply observe, to compare these two neighbors, to compare how much of the indices I1 to I10 and J1 to J10 are the same, are in common, okay? So essentially, how many points are close to the first point every time we represent it in representation L or in representation M, okay? In particular, these can be then averaged over all the data set, and we essentially take out the probability of neighbors of a point to be preserved into different identity of the neighbors of a point to be preserved into different layers. And in particular, we interpret this essentially as the fact that if we have a very, very high percentage of points which are closest both in one layer and in the other to a given point, then the local distribution of points is very, very similar, okay? Of course, distances can change, but the relative position is kind of preserved. So this describes the first formula, while the second is slightly more specific in the case when we have a ground truth classification. Let's imagine ImageNet, for instance. So we have a subdivision in cats, dogs, boats, etc., etc. So essentially, this measure gives you the probability that if I take a dog, the closest k neighbors, where k is fixed and maybe equal to 10, are going to be dogs as well, okay? Or the probability that if I'm considering a point which is a cat in a given layer L, what is the probability that my nearest neighbors are also cats, okay? These are the two quantities that we measure in order to assess the changes in the geometry of transformers. Of course, we are not the first to study this, and this is not the first study in the context of deep learning. Much work has been done in the context of convolutional neural networks, for instance, by Alessio Ansuini, our collaborator, and also by other groups around the world. And what can be observed is that essentially, and this plot is quite crucial because we're going to see many of these plots again, so I try to explain it a little bit in depth. So if we look on the x-axis, essentially, as at which number of layer I'm considering inside the network, which is rescaled between 0 and 1, because we want to compare networks which have a different number of layers, okay? Some are deeper, some are shorter. For instance, if you have a ResNet 18 or a ResNet 152, of course, they're going to have a different number of layers. In order to compare them, we rescale the numbering of the layers with respect to the total number of layers. So essentially then for each layer, what we do, we put a dot where on the y-axis we have the intrinsic dimension of the representation of our dataset in that layer. So for instance, I take the ImageNet dataset, I do inference on the whole dataset using, for instance, ResNet 152, and then I collect representations at the various layers. Once this is done, for each layer, I will use the 2NN method developed by Lio and others to compute the intrinsic dimension, and this is the plot. What we can observe is that intrinsic dimension first increases and then decreases, but taking this famous Henchback shape. Furthermore, the compression at the last hidden layer is related to accuracy in performance. So the most information is compressed. So the lowest the ID, the more accurate is the essentially performance. Okay. The way in which this has been interpreted in the literature is making reference to the kernel trick. Of course, we're trying to classify images, so we're trying, at the very end, we're trying to linearly separate different classes using a linear classifier. So the idea is that in this first part of the network, what implicitly during training the model is learning is to play the kernel trick. So it's learning some smart kernels to send data into higher dimension, which are before lying into low dimensional vector space, into higher dimensional vector space, in order to explore the features which are then the one necessary, that then are discriminated, keeping only the necessary one in order to perform classification in the last part of the layer. The local geometry has been also studied in this context in other works, in particular by Diego Doimo and other collaborators. And here, what has been found is that in the case of convolutional neural networks, first of all, essentially the local geometry and the global geometry are not related at all. So in principle, one expects that if the dimension is increasing, there is a lot of change in the local geometry, and vice versa. If the dimension is decreasing, there is less modifications, and here what the findings are rather not as expected. And on the other hand, if you look now at the question that we were asking before, now we have ImageNet classes, so we want to ask how likely it is if I'm a dog that my 30 nearest neighbors are also dogs. The information arises only in the last few layers of the network, okay? So we're starting, the information is starting to arise only basically at layer 142, you have less than 2% that the dog next to you is also a dog. While at the end, the information, of course, is very, very high because we need to classify. So 80% of the dogs next to you, images next to you, sorry, representations of images next to you are actually dogs. So what we do is we play this game of studying these two quantities in large transformers. Large transformers trained on one side on protein sequences with the mask language modeling, and on the other side on images using basically next token prediction, next pixel prediction task. Okay, the curves that we find are the two shown in this plot, and I'm going to try to guide you in interpreting them a little bit, starting from proteins. First of all, the color code. Okay, the plot is the same as before. So on the x-axis we have the numbering of the layers, on the scale, and on the y-axis we have the intrinsic dimension that we measure for a particularly relevant data set in the context of protein, which is called protein net. I'm not going to go further into detail with that, but still it's a very well established data set. And we look at the dimension of representations of this data set. We look at them for models which are essentially the same apart from the size. Okay, so all of them have been developed by Meta. They're called this ESM2 family, but they range from 8 million parameters to 3 billion. So there is a large range of sizes. And what we can see is a sort of emergent phenomenon. If you look at models with very low number of parameters, essentially we cannot see much change. There are not many changes in the at least globally in the geometry. While the more the model increases, the more we get to this final shape, which we can intuitively divide in three parts, where we have first a peak, okay, in this first part, a peak, a plateau, because essentially dimension is not changing very much, and then what we call a final ascent. So let me do some few observations. First of all, the peak, of course, we relate it to what we saw before in the case of convolutional network. Here, the role of these layers is the one of exploring features, and then encoding only the ones that are strictly necessary to solve the task, which again is a task completely unrelated to biological properties of proteins. It's just a task to predict missing amino acids. And then let me discuss the last part where the dimension is still growing, getting back to the original dimension. Why it's still growing? Because basically we're locally trying to, when we predict missing amino acid, we're locally reconstructing the data. So eventually we should end up with the same dimension that we started from, at least approximately. While in the last part, in the middle part, what is important to stress is the fact that, first of all, Dimension doesn't change much for a few layers in all sufficiently large models. And it's the part in which the model mostly compressed data. So we have the lowest dimension possible, which is even of course, the values are not so relevant because they depend on the exact values are not so relevant because they depend on the choice of the dataset. But the relative value between the models is the fact that they converge to the same value is very, very much important, saying that essentially there is a sort of convergence, universality in the ability to compress data in this type of models. Okay. The case of images, the shape is a bit different, but again, we verified that there is an initial peak for feature exploration and a relative minimum in the middle, in the intermediate layers, and then dimension grows again, at least and grows much more with the second peak. The more is large, the larger is the model, because again here we start from the yellow one, which is IGPT small, growing to IGPT medium orange, and red IGPT large. For the large model, we can see a relatively prominent peak that then comes back to the original dimension. Okay. So eventually, what we want to understand here, the most important thing that we want to understand here is why the model compress data autonomously without anyone having to, no one ever asked the model to compress data because it's transforming data in the same, the embedding space still carries the same dimension. So why the model and what can we exploit from the fact that the model is behaving as a sort of very sophisticated and autonomously developed autoencoder. Okay. The second thing we do is compare global and local geometry. So here, the plots in the bottom show when you compare layers one to the next. So for instance, layer, the embedding layer with the layer after the first self-attention block, how much the neighbor were rearranged. And we can observe that in the first part there is quite a drastic rearrangement. At least this is absolutely evident in the case of protein. While in the plateau, essentially, we have not much. We have not at all. We can almost not at all observe any local rearrangement. Okay, this is less evident in the case of images because the changes in the layers are much more gradual apart from the first and last layer, but still the low encoded, the relative minimum still has a quite high neighborhood overlap. Okay. The next thing we analyze, which I find quite interesting, is we try to understand. Now we take models that we fix the model, let's say ESN2 for a given number of parameters. This case is 650 million, and we try to understand that during training how the ED profile changes. Okay, so at the beginning, the color code is the darker the most we go in training, the most iterations we did during our training procedure. And you can see that when we start, the ID curve is essentially flat. With this very light blue, is essentially flat. It's flat because we have random transformations, so it's expected that the intrinsic dimension should not change very much. When we start training and then we go to darker color, the first thing that emerges is the fact that there is the development of a peak in the first, let's say, 30% of the layers. But still, there is not evidence of a clearly well-defined plateau, and even less of a sort of final ascent. The more we go in training, the more the plateau becomes evident, and the more we're able. So the more we compress in the intermediate layer, the more we are able to reconstruct locally the inputs to predict missing amino acids in the output layer. Analogously, we can observe similar behavior in images, where first there is the development of the first peak, and only after the intrinsic dimension decreases in this relative essentially showing this relative minimum, and the final smaller second peak arises. Okay, so somehow we can detect a sort of hierarchy during training of geometric behavior inside the layers of this network. But why are we so interested in these low-dimensional representations? Because our suspect was that these were the most informative representations of the data. And in fact, this is confirmed when we consider datasets that now are annotated by semantic classes. So in the case of protein, we take a bunch of proteins which are divided in groups depending on their structure, essentially. And in the case of images, instead, we take ImageNet, where we have images which are classified in images with the same semantic content, so dogs with dogs, cats with cats. And we check at every layer of these models how many of the neighbors are in the same class. Let's start with protein. So basically, if we look at the first layer, and we take the representation of a protein, we look at its name, at our neighbors. Essentially, there is no reason to believe that the neighbors are belong to the same structural family. So the structures are going to be unrelated. But while we go along the layers of the network, we can appreciate that in the layers of the plateau, so these layers here in the second last part, the information of fold emerges automatically. Again, I want to stress that these models are trained by self-supervision, so they're not informed at all about structure whatsoever. And this is more evident the more, and the information is better, of course, the more the sizes of the model increase, okay? So the larger the models we take, we consider, the more the information of folding emerges. It's also important to notice that in the last few layers, the information degrades, because of course, the last few layers are strictly employed to solve the self-supervision task. So this is not abstract. What we care about in the last few layers is not abstract semantic information, but it's the details of reconstruction, which eventually are not necessary or important to solve tasks such as recognizing the fold. This comparison is even sharper in the case of images, where we have only one local maximum appearing exactly in the layers where we have the minimum, the relative minimum of the ID, in the intermediate layer where alignment with the ImageNet classes is maximal. Of course, the level is very low because the model has not been trained to detect classes, but still, in order to predict the next pixel, the belonging to a certain class is not irrelevant, and we can observe it here at the 40% of the layers, where we get a signal of the fact that neighbors predicts at least at a certain extent class belonging. Okay, so if I look at neighbors of dogs, these are actually representations, the neighboring representations of a dog. These are typically, at least with the 35% probability, dogs. Okay, but now I promised that the talk will start with language and end with language, so I want to present you just a couple of recent results that are still under development, which concern basically the most popular publicly available architecture, which is this recently developed Llama 2, for which the largest model is approximately 7 billion parameters, and that has been shown to have performances in generating text similar to at least GPT-3. And I want also to stress the fact that, okay, here we see a plot that I'm brutally stealing from the Llama 2 paper, where we see basically learning curves, or the measure of perplexity during training for different number of models with different number of parameters. And what I think is quite crucial to observe is that the authors stress the fact that these models did not even reach saturation after seeing 2,000 billion tokens. Okay, so what we see is now it's starting to be a reasonable picture but it's still for sure not the definitive picture that the D profile of a large language model is going to be looking like once full training has been done, or once the models have been considered to be even larger. Okay, I want to show this because the reason of our delay in approaching language is mainly due to two reasons. The first is two motivations. The first is the fact that the dataset for language is enormous, so the number of parameters that you need in order to fit decently the data, at least, is enormous. And here you can see this here in the numbers of Llama 2. But also the fact that somehow all the phenomena that we have observed also for proteins and for images are emergent phenomena. So we need a sufficient large number of parameters compared to the size of the dataset in order to observe reasonable behaviors. Okay, and so now I'm just going to show you the results that we have, and these have been measured on a dataset that is we denote as IMDb, which basically it consists of movie reviews which can be classified in positive, negative, or neutral. And on the plot on the left, you see essentially for different scale of the Llama models, you see intrinsic dimension measured at different layers. Okay, so here we can see an increase at the beginning. Then of course we consider the more stable the one with more number of parameters. So we should focus on the red curves. So there is an initial increase in the intrinsic dimension. Then we have a first plateau that is followed again by a second plateau and then a slight ascent at the end. Okay, so here we don't have full reconstruction. But this is quite reasonable given that the fact that the perplexity on text data is keen to be much higher than the perplexity that we have on protein or images, where essentially in proteins you are choosing among 20 amino acids, and in images the number of colors are quite few, while here a model must choose among a vocabulary that is extremely large, okay, in the order of thousands. Okay, so this is perfectly justified. Again, what we compare to now is with the following. We check basically for various layers how much is likely that the neighbors of a positive review is a positive review, and likewise for the case of negative reviews and neutral. Of course, we start from a higher level than what we observed before, because we have only 3 classes, so the problem is easier. But still, it can be appreciated that the maximal information, at least in the largest model, arise exactly in the presence of the first plateau. So this plateau here on the left, the first plateau here on the left, corresponds to the maximal performance in detecting the same class when looking at neighbors of a certain data point. Okay, so before stopping, I just want to give a couple of words on what are some of the things we're working on and we're interested in. Of course, I already say that text will need much more in-depth analysis, because we know that the hierarchy in which essentially information is encoded in intermediate layers of NLP transformers is much difficult and delicate. There are also like some, at least partially controversial results in the literature. Not controversial, but let's say it's not easy to detect which type of information is emerging and what is the hierarchical organization. That is instead much more easy in the context of, for instance, convolutional networks to understand, for image classifications to understand. Okay, so for sure we'll be doing a lot of analysis on text, and in particular we want to understand what is the role of this second plateau that I was mentioning before. While in the case of protein, we want to understand what's going on in these plateau layers. Okay, we want to ask if we're not seeing many differences only because we're looking at too coarse information on the geometry. So if there is some other measures, maybe topological or for some other kind, that can give us more insight. Or otherwise, from another point of view, we want to measure how much these representation here are universal, because somehow they are really, really conserved from a certain number of parameters on in terms of dimension and local composition. Well, in the case of images, we'll be probably focusing our attention in the emergence of the second peak, which certainly plays a role, because of course, the larger the model, the better we are at predicting pixels and generating images using IGPT. So for sure, this second peak has a specific role that we want to identify more clearly. And I just want to thank you for the attention and showing the plots of our collaborators. Again, Lucrezia here in the middle, Francesca and Diego up on top, and Alessio and Alessandro on the sides. Thank you very much.
Thank you. Thank you to you, Alberto. Super interesting. We have just a few minutes for some question, if any. So feel free to unmute yourself and ask to Alberto any question. I can start as an icebreaker. So I was wondering if from one layer to another, it's possible to have a change in the topology of the shape of the manifold, and if you find out some topological invariant shifting from one layer to the other, then I will leave a question to others.
Okay, this is a fantastic question, Cristiano, of course, because it's leading to some of our current investigations. So thanks for that. In fact, what I come back to a slide before. So what we are trying to understand now is if using some techniques which go in the realm of topological data analysis, which is a kind of now relatively well-established technique in the analysis of point clouds. If, in fact, in the layers of the plateau, we can observe some changes in the topology. First of all, I want to mention that there are some works in the literature that already explore essentially behavior in some topological invariants inside hidden layers of neural networks. I don't think of transformers explicitly, but somehow already persistent homology was related to performance and other properties in neural networks. And yeah, we're actually trying now to study the best way to compare topology in successive layers of neural networks more abstractly and more empirically, basically to compute persistent homology in the plateau layers of these transformers to understand if something hidden is going wrong, okay? And we actually there is a researcher that recently joined our group, Matteo Biagetti, that is kind of an expert in persistent homology, so he's going to help us in this direction.
Okay, thank you. So interesting. Thank you very much.
So we suspect that. Let's say we suspect that, but we're not so sure.
Okay. If there are any other questions, feel free to unmute yourself.
Alberto, I have another question for you. Thank you so much for the talk. It was really interesting. I didn't quite understand the point where you were talking about semantic richness. So you said lower dimensions tend to have more semantic richness. Could you explain that a bit?
Okay, of course. Speaking about semantic richness, so generally is not so polite in a sense, or like precise. So in a sense, you should imagine like if I had to give you a suggestion on which layers to choose to put a linear classifier for solving a task, which is related in a sense to the semantic of the data, I will choose data where the hidden dimension that is measured, representation where the hidden dimension that is measured is lower, okay? So in particular, in the case of IGPT, if you want to distinguish classes in ImageNet, and this was already actually in fact shown by OpenAI, basically the layers you should look at are these ones here. Let me show you the slide. are these ones here. Okay, this fact that the most informative layers were the one here at 0.4, basically at slightly before the half of the network, was already shown by OpenAI. What we show is that if we didn't have this information, we could basically predict it by just looking at the dimension. Okay, and this is useful because eventually what is good about transformers is that you don't need labels. Okay, so you don't need labels, but then you want to understand eventually something which is related to labels, maybe. Okay, so
right.
it gives an unsupervised way essentially to detect which are the most informative layers. And in fact, in the case of proteins, we did exploit that because people were doing this classification, looking at the last layers, and basically doing the same operation, just a handful of layers before, maybe 6 or 7 layers before, you improve performance by 7% or 6% for free. Okay, and in that case, we didn't know that a priori. We just infer it by our analysis on dimension. Okay, so this is the main message of the talk.
Yeah, that makes much more sense now. Thank you.
Maybe Francesco had a question.
Yes, I have a question. Can you hear me?
Yeah, sure.
Yeah, so my question is simple, and it's are there differences in how these plots look like when we use different optimizers, or are they invariant?
Okay. Well, I should think about that. I'm not so. I mean, I'm not so sure anyone ever considered these. I mean, I tend to think about these as much broader type of invariants. Okay, so these are heavily influenced. I mean, this is what we're speaking about macro scale. Okay, so this is influenced by the data sets you use, the architecture you use, the task you employ. Okay, for instance, you can show that if you take a transformer and you use it for classifying instead of for self-supervision, okay, the plot does not look the same. At the level of optimizer, of course, there are slight differences, but I mean, if the model converged and converge properly, I do not expect these to lead us to large differences, honestly. But maybe in a sense, I mean, I'm being a little bit, this is very speculative, okay? So maybe we shouldn't record this.
No, that's okay. I'm just listening. I'm curious.
Maybe, and we cut this afterwards, but maybe you can use some of these to try and infer some information about how much your optimizer is doing well. But of course, you're going to be looking at the loss. So typically, judge an optimizer here, you will discuss about, you will look at perplexity. Not so sure the tight relationship between ID and optimizer, but I mean, maybe there is, okay? Maybe there is.
Yeah, I'm just going to give you why I asked this question, and it's because something similar, I would say, something that we were trying on extremely small neural networks that we could optimize with second-order optimizers, which are completely unfeasible for anything like for any transformer or anything like that. But I've always been curious about how those behaviors that you can get from second-order optimizers that were activating in the weights in a very different way in my previous experiments, but on like if anything like that has been explored in.
It might be, and maybe something I can point to. If I point you to something in the literature, okay, there are two perspectives on intrinsic dimension. We take one, which is we look at data and we look at the representation of data. There is another one, a dual one, which essentially measure the dimension depending on weights. Okay, it's a sort of dual construction. So perhaps I think that could be interesting in your case, and I can even lead you to a paper where this quantity has been studied in the setting of transformers for NLP, not so recent, but not so long time ago. I don't know, just drop me a message and I send you the paper, because maybe it might be interesting in trying and look at something like that.
Okay, I'll send you an email right after this talk.
Yeah, thanks.
Thank you.
Okay, thank you, Vision, Francesco, for the questions. And if there are no other questions, I thank you again to Alberto. Maybe we are going to invite you, I don't know, next year to have some updates on this research. And stop. That's all. Thank you also to everybody that joined us in this tech talk. Next one will be at the end of the 30th of August, if I'm not wrong. If you are following our social media, you will be updated. And so see you in 1 month. Thank you again to everybody. Thank you, Alberto.
Thank you, guys. Bye-bye.